We present our work, an analysis of unified manipulation with robot arms and dexterous hands via optimization-based motion synthesis. Complex manipulation tasks can require coordinated motions from the entire manipulation system, including the robot arm and the dexterous hand. One immediate challenge of this strategy is the high kinematic redundancy of the system, because the same object motions can be conducted exclusively with the robot arm, or with the dexterous hand, or a combination of both. To effectively evaluate the benefits of unified manipulation, we use an optimization-based motion synthesis framework, which for a given goal object pose finds the joint angles of the robot arm and the manipulation actions from the hand at each time step. The motion synthesis framework also maximizes the configuration quality at each time step by optimizing for goal pose accuracy, singularity avoidance, collision and joint limit avoidance, motion smoothness of the joints and the grasped object, minimal joint torque, and required hand manipulation actions. We adapt a motion generation framework that optimizes the sequence of configurations over time. The objective function for this optimization is defined as a weighted sum of these attributes that collectively define the configuration quality. We then use this motion framework to experimentally evaluate unified manipulation with robot arms and dexterous hands with two optimization weight versions, one that prioritizes matching the goal pose accurately and another that emphasizes the motion smoothness of the joints and the grasped object. We use two robot arms in our comparison, a redundant 7-DOF KUKA arm and a non-redundant 6-DOF UR10. Each of these arms is tested with 5 different robot hand models with a wide variety of manipulation tasks. An example task is shown here being carried out by the same optimization weights and robot arm, but with different dexterous hands in each case. The manipulation actions of the hands determined by the motion optimization framework are also shown at each time step. Various arm-hand combinations with two versions of weight options are evaluated on 5 different experiment tasks. The goal paths for each task are discretized and even have additional collision geometries in some cases. The first task serves as a baseline gradual path absent of any obstacles. The second task demands the object to be guided on a path with abrupt changes in direction, which may induce large joint motion changes. The third task requires the robot navigate walls and shelf obstacles to reach for the red cup and then pour it over the green bowl. The next task requires the robot arm and the hand to trace the letter ICRA while the arm is caged in with walls on all 4 sides. The task is nearly impossible to execute without any collisions. The last task path simulates a precision manipulation task, where the object is required to be translated and rotated in all 6 principal directions by small magnitudes at different points in the system's workspace, indicated by the black circles. Through these evaluation tasks, we can quantitatively characterize the benefits of unifying arm and hand capabilities within a single motion model via metrics such as pose accuracy, manipulability, joint space smoothness, distance to joint limits and collisions, and more. The aggregated results shown here suggest that combining motions from the arms and hands indeed has compelling benefits, highlighting the exciting potential of continued progress in unified arm-hand manipulation. Thank you.